Okay, so indeed, in order to avoid having a gradient that is very sensitive to the random action sampling, we use a well-known trick. It's originally presented in variational autoencoder. I'll show you some of the roots of this trick in a second, but we use it in this case. This helps a lot stabilize the gradients and, as a result, the learning process. So what we do is a pretty simple trick, but it's very helpful. We define a hard policy function instead of our soft policy function, which we call f, and it has the same tunable parameter. It's f of this phi, right? But this function takes both a noise vector, I'll define that in a second, and a specific state. And what does it output? It outputs the mean value for that state plus sigma, the covariance, the variance of that state, multiplied, sorry, not the variance, the standard deviation of that state, multiplied by this randomly sampled noise. So, by the way, this is exactly how we define a random a normal distribution, right? A Gaussian. So the only thing that we do is pushing the randomness away, right? We assume that we get as an argument the noise, some noise parameter, and we use that in order to compute the output of the Gaussian. Okay, but this noise is not part of our policy, but it's given from an outside source. So now, our loss function is similar to what we saw before, but the policy is now a function that is defined through f, and, the action is not randomly, the action that we're considering is not randomly sampled, but it comes from this deterministic f function. I know that the epsilon here is randomly sampled, but we'll get into that in a second, because the interesting part is that we won't need to compute the gradient for this random process. We'll see this in a second. And again, minus the q value for that deterministic action this time, right? Having the same epsilon. And so the gradient can be defined as follows, right? Also following the fact that we're not sampling an action, but we have a very specific action that is deterministically drawn using the f function. And now the action at any time step is defined by our deterministic function f. Our soft policy is defined implicitly by the deterministic policy. And the epsilon, the noise vector, well, it is a noise vector that is sampled from some fixed distribution. When we assume a fixed noise instead of a randomly sampled action, it will allow us to compute or to have a lower variance in the gradient estimators for both mu and sigma. Okay, so that helps a lot with stabilizing this process. I'll quickly give you some background on the reparameterization trick and where it's used. But this is a bit of a side note. I'll just explain for what reason it was developed. And that might help you understand why it's useful in our case. So, the reparameterization trick was originally presented for training variational autoencoders, where the loss function for variational autoencoders is defined as the difference. So I'll quickly write the autoencoder. We're trying to train an encoder and a decoder to encode some input, usually image, and output the same image. But once we do that, we compress all of the data to some lower dimensions, and that in principle helps us to generate new new instances from the same distribution. Okay, but in a variational autoencoder, we also use a random process where we encode all of the input into some Gaussian, and then when we randomly pick a value from that Gaussian, we are able to reconstruct our original image. Well, that's what we hope to train our encoder, and then later on we throw away the encoder and we can generate new instances from the same distribution. That's the idea behind the variational autoencoder. However, when we train variational autoencoder, we use the backpropagation algorithm, the backprop algorithm, as we've seen before, and we backprop our loss through the network. However, when we reach the random process, the random sampling portion of our network, well, then we get stuck because we cannot compute a derivative of a sample operation. So instead, the trick is very simple. What we do is we add noise separately as a parameter to the network that can be randomly picked from a Gaussian, specifically if we're looking to represent a Gaussian. And then we have a deterministic combination of sigma and mu that produces the next layer, the next activation in our network. And once we do that, and we consider the noise as sampled outside of the network, and all of the propagation, the forward propagation in our network as a deterministic process, then we also can easily apply the backprop algorithm. Of course, the backprop algorithm does not include now the sampling process. Okay, so this is just in order to complete the picture here. Now, variational autoencoder, if we train them this way, now we can easily generate new instances from the same distribution that we haven't seen before by randomly picking a noise value, and then we can generate new instances, even those new ones that we never saw before.